Greetings, student. This is a recording of one of Garnett's online math lesson classes. You have been granted access to watch this video because you're a paying student and I have seen it fit to provide this recording to you. However, it is important that you know you're not allowed to share this video with persons outside the lessons. This policy is so that my services are kept only to my students. Thank you, and I do hope you enjoy and learn from this video.
We move on to a new section of the syllabus, and it's called J-circle theorem. And this is, I can say this is one of the a topic that CXE likes, right? You could say it's one of their favorites, right? Circle theorem. They like to bring circle theorem. So there's a ton of past papers out there where you can get practice from doing circle theorem. And we will do some practice looking at circle theorem questions straight from the CXE paper 2, right? It comes in the paper 2. Good. So theorems, if you never heard the word theorem before, theorems just refer to a fact, right? Some fact. One theorem is the sky is blue, right? That's a fact we've all come to know and live with. Theorems are more of axioms than I want to say facts, because theorems are one of the axioms, but let's just think of them as statements that are true, right? Theorems are just statements that are true, and you can use these statements to come up with certain conclusions or to solve something. One theorem that I know all of you are already familiar with is that the internal angles of a triangle add up to 180, right? That's a theorem, right? And that one, you use that to solve particular problems, especially if you want to know, you have two known angles of the triangle and you want to know what the other side is, you can simply just use that theorem and get the other side. So that's what we're going to learn today, some theorems about the circles, right? About circles. And laid out before you is the content, how we will cover this topic. And the first thing is for me to remind you of properties of a circle so that the terminology again doesn't confuse you. Good. So let's look at me. First things first, you don't need to write any of this. I'm just reminding you of these properties of a circle, these terminologies, these terms that you're already familiar with. And those are the 4 common ones that you've known since primary school, and the less so common ones that you've more or less been introduced to at this level, right? So first off is the circumference. We know the circumference is the outline of the circle. The radius, just remember the radius is a point drawn from the center to the circumference. As soon as you see these things, you got to be able to pick out these properties of the circle. They will apply to the theorems, right? Certain theorems will use these terms, and that's why I'm bringing them up and reminding you, right? So look out for radius, look out, well, you know, the circumference. Look out for diameter, look out for semicircles. I remember the semicircle is just when the diameter splits when a diameter is drawn, it splits the circle into 2 semicircles, right? Half and half, 2 equal halves. Next, we have the arc. Remember, the arc is just a portion of the circumference, And next, we have the chord, and like I explained, the chord is like a diameter. However, it doesn't pass through the center. And you could think of a diameter as a type of chord. But just keep in mind that a chord is a line drawn from one point of the circumference to the other. A straight line, of course, drawn from one point of the circumference to the other. Next is the segment. And when we draw a chord, it splits the circle, it split the circle into segments, minor and major segments. Same like how the diameter splits the circle into semicircles. If it's not too perfectly same side, if not perfectly split into 2 halves, then it's just split into 2 segments, a minor segment and a major segment. Next is our sector, and this is of course pizza slice, analogous to pizza slice. And a sector is bounded by 2 radii and that arc. A portion of your circumference and 2 radii, give you a sector. And of course, once we have a minor sector, there will be a major sector. right? Just remember those properties, because when we look at these theorems, these are the things we're going to be more or less bringing up, right? To help you remember the theorems. And these are the words you will be seeing, right? For those of you who have not looked at circle theorem before. So there we go. Good. So now a new property that might be new to some or an old friend to some is the tangent. So you gotta remember, you gotta do what a tangent is. So a tangent line is a line that touches the circumference, an external line, I should say. It's an external line, right? Meaning that's outside of the circle. So the tangent line is a line that touches the circumference of the circle at one point only. It only touches the circumference at one point. So let me just add this into the definition. Is instead of A, we're going to say an external line, right? And that's why it differs from it's outside. Good. And here is a nice illustration of what the tangent line looks like. So here we have a circle, and then we have a tangent line. I remember tangent line is any line that just touches the circumference at one point. And of course, it's outside, right? So this is a tangent. This is a tangent. These are tangents, right? These are what we call tangents. They're tangent to the circle. Matter of fact, they're tangent to the radius join. Anyway, we look at that when we look at theorems. The word tangent actually means, right? This, however, these are all tangents, right? Any line drawn, don't let the number of line confuse you. Once it's, just isolate them, right? Once it's a line drawn and it's just touching one point of the circle, each one of these are just touching one point of the circle. It's touching the circle once, right? That's another way to put it. Once the line just touches the circle once and it goes all across, it's not intersecting, it's a tangent. Tangents don't intersect circles, right? So don't ever look at any line intersecting the circle and call it a tangent. And a cool point to note is the point at which a tangent line touches the circumference is called the point of tangency. And that's what the second statement is saying here, right? Because our tangent line only touches the circumference at one point only, and this point is called the point of tangency or the point of contact, right? That's the point at which it touches, the tangent touches the line, right? So this is not a tangent. However, there is a name for it. However, we're not interested in these kinds of lines, right? Lines that intersect our circle. There are names, and this is okay. Let me not add to that. But this is not a tangent. It doesn't qualify as a tangent because it goes through our circle. Our tangent needs to only touch one part. And this is touching the circumference at two places. So you might argue, okay, if I just draw a line like this and stop, this should be a tangent. No, it's not a tangent. Yes, it's only touching the circle at one point. However, it's still intersecting into the circle. And if I was to continue this line, it would inevitably touch the circle at 2 points. Tangents do not do that, right? It only touches the circle at one point. Whether it can go on for infinity, it will always just touch our circumference at one point. And that point is, as I said before, called the point of tangency. So just take some time to take note of this. All right, first theorem, and these, first of all, what I want you guys to remember the theorem, not the theorem number. Right? Fair warning, any one of them could be theorem 1, any one of them could be, any one of our 9 theorems could be theorem 1. So don't focus on the fact that this one is, I have this one labeled theorem 1. They can be in any particular order. That's just the order that I place them in. So what you need to focus on is memorizing the theorem themselves and not the theorem number. Right? And you don't need to remember the theorems verbatim. By that I mean word for word. You more or less just need to get the gist of it, right? Once you get the gist of it, when you see some examples, you have to actually state what theorem you use. That's what you write. What you remember about the theorem is what you write. Right? This first theorem, which we're calling theorem 1, says that the angle at the center of a circle is twice the angle at the circumference standing on the same arc. A few terminologies there that we need to be, that I reminded you of, and that is circumference and arc. Right? Well, you know of the circle. But so an angle at the center of a circle is twice the angle at the circumference standing on the same arc. So what to pay attention to is that the angle at the circle at the center is twice the angle at the circumference, and they need to be standing on the same arc. So this is the criteria we need to check, right? So an angle at the circumference, here we have several circles so that you can see them in several different scenarios. I need to correct this. This is fine. But so here we have 3 different scenarios, and each one of these scenarios will apply this theorem. I remember these are just statements that are completely true. We can use that we're going to use to solve. So here we have the first circle we have is an angle, right, that is placed on our circumference and an angle at the center. Please note that the O here is our center. Let me actually mark this permanently here. It has the animation with it. Good. So this is the center of the circle, and that's what we're going to label O. Right? Now, what this theorem is telling us is that any angle at the center of the circle, and to identify that an angle is at the center, the 2 lines, we're going to call them the angle lines. Every angle has 2 lines, right? That's how angles are created. Right? 2 lines connect to create an angle. So once those 2 lines connect at the center, we say it's an angle at the center. Right? Going that over again, the 2 lines create an angle. Right? Breaking this down very slowly. But yeah, 2 lines create an angle. Without 2 lines, we don't have an angle. Right? If we only have 1 line, this is an angle. Right? This is an angle, but you can argue that the line is actually like this. Right? Here is the center, and there are actually 2 lines, but they are co-current lines, meaning that they're on top of each other or connected to each other, right? So we can have lines like that. Nevertheless, 2 lines need to constitute an angle. And if those 2 lines connect to the center of the circle, meaning it's like this, then it's an angle at the center. And that's what we need to, and that's how you identify whether an angle is at the center, right? If the angle indeed at the center or our line constituting this angle comes together at the center of the circle. Good. So this is an angle at the center, and it's labeled X. And using the same analogy, this is an angle at the circumference. Reason being because, of course, the angle connects to the circumference. And for all your circle theorems, what you're going to be identifying is where your angles are. It's either going to be at the circumference or the center, right? And be careful, not all of them are going to be at the center. Right? So from now going forward, always check to see where your angle is. If it's on the circumference, if it's on the circle. Of course, our theorems will apply accordingly. Good. So 1 angle at the center, 1 angle at the circumference, and this one is labeled Y. So from this theorem, it says the angle at the center is twice the angle at the circumference standing on the same arc. So we know this is an angle at the center, sorry, and this is an angle at the circumference because again, the 2 lines constituting this angle connect to this at the circumference, and they're standing on the same arc. they're standing on the same arc. And remember, an arc is a portion of our, I'm going to use black here. An arc is a portion of our circumference. And what we're going to look at now is the line that constitutes these angles, right? That's what we're going to be looking at all the time. So they're standing on the same arc, which means by definition, the angles that the lines, that constitute this angle stand on the same portion of a circumference as our center angle, right? They're both standing on the same arc. They're both standing on the same piece of the circumference. Right. Good, and that's what it says. So once that is true, so once we have an angle at the center, angle at the circumference, this theorem tells us standing on the same arc, sorry, forgot to say that, they're on the same arc. You could say they're on the same chord. In some cases, you might say chord instead. And just so that you know, we can actually draw a line from here where these two angles are standing. This is what they're standing on. You can actually draw a line across here, a straight line across here, and this would actually be a chord, and they would be standing on that chord. So that's all we need to look at. Good. Good. So we have our circle. We identify that these two angles are indeed standing on the same arc. And one is in the center, and one is at the circumference. This theorem says that the angle at the center is actually twice the angle at the circumference, meaning that twice just means 2 times, right? 2 multiplied by. So what that means is that angle X, right, is actually 2 times Y. So that's that's the explanation for this theorem. An angle at the center is twice the angle at the circumference. Of course, provided that they're standing on the same arc. If they're not, then can't. Right? This theorem is null and void. So these criteria need to be met. One needs to be standing at the circumference, not standing. One needs to be at the circumference. One needs to be at the center, and it must be standing on the same arc. Right? That's the portion, this portion of the circumference that they're connecting to. Good. So once that's satisfied, this theorem, we can use this theorem. Angle at the circumference is X. Angle at the center, sorry, X is actually 2 times the angle at the circumference. And that's what these two equations are telling me. So if X is twice of Y, then Y is half of X. Right? That there is basic analogy. So if X is 2 times Y, then of course Y would be half of X. Same thing. So you can actually write this and say that the angle at the circumference is half the angle at the center, standing on the same arc. Right? And that's another way you can rewrite this theorem and call it theorem 2. But it is the same theorem. Right? It's technically the same theorem. And we don't want to confuse you and do that kind of thing. However, you got to be able to make that connection. But if I have, doesn't matter which angle I have, I should be able to get the other one by either multiplying it by 2 or multiplying it by 2 or dividing it by 2. You got to know which one you got to do. Just remember which one is twice of which. The one easy way to remember it is that the angle at the center is always larger. So that means you got to multiply our angle at the circumference to get the angle at the center. And we got to half the angle at the center to get. Right? So the angle at the center is always larger than the angle at the circumference. You can use that to remember which you need to multiply it by 2 or divide. Or just remember the theorem. Good. So this is the first scenario. In the second scenario, it's the same thing. However, again, take your time, identify where you are. Okay, that's an example if Y was 50. Good. So again, take your time and identify where your angles are. And your angles will only be, honestly, your angles will only be in two places, either in the center of the circle, at the center of the circle, or at the circumference, right? So first, we know that angle X is at the center, right? Angle X is at the center of the circle, and angle Y is also at the circumference, right? So we identify an angle at the center and angle at the circumference, and they are standing on the same arc. Now, what happened there, right? The arc they're standing on is this portion of the circumference, not this portion, right? Good. And this is something that that could catch you off guard. Sometimes you could be a master at circle theorem, but if this never comes up, something like this never comes up, then you could go your whole life not knowing this. But for any angle to be standing on an arc, it needs to be facing that arc, right? So the reason why, even though one might argue that, okay, these angles, both of them, the lines that constitute both of these angles are connecting at our circumference here and here, right? I'm just looking at where these lines go, right? This is our angle. I'm looking at where these lines are, right? These lines here. Good. So it's here and here, but you might argue that why they're not standing on this part of, why can't I say they're standing on this side of the arc? They're not. They're actually standing on the one that I had there before in green. This is the arc that they're standing. This is the arc that they're standing on. So you have to go all the way around. And the reason why is because our angles are actually facing in this direction. In this direction, it's here. So I can just come down. This is the arc here that they're standing on. In this direction, it's here. And one of the reasons why I want to point that out to you is because if the angle, if instead of the angle being here, I actually threw the angle here and put X. And you might say, okay, well, this is an angle at X is an angle at the center, and I can't argue with you there. This angle is indeed at the center. This angle is indeed at the center, but this angle is also at the circumference. I go to this arrow. But this angle Y is at the circumference again, because here, right, it's at the circumference. So X is still at the center and Y is still at the circumference, but these two are not standing on the same arc. Reason being because the one in red, X, let's use all red for X. X is facing in this direction, hence it's actually standing on this arc, right? And Y facing in this direction is actually standing on this arc, this portion of the arc. Yes, they both connect to the angle. Right? Yes, they're both standing on a portion of the circumference. It almost looks like they're standing on the same arc, but they're not because of the direction, right? So always keep in mind that for an angle to be standing on an arc, it needs to be facing that arc, right? That's how you double check to ensure. So because these two angles are actually not standing on the same arc, then this theorem is null and void in this situation, right? So students would get mixed up in this case, right? And multiply this by 2 because again, you have an angle at the center, angle at the circumference, more or less connected to the same arc, but and you would think you can use this theorem, but you can't, right? You can't use this theorem in this scenario, right? So be careful with that. Let me know if you get it. And we have our last scenario, but so you know this. So right away, again, the further scenario, like X is actually luckily facing in this direction. This angle here is facing in this direction. In this scenario though, because this scenario actually probably is going to come up in one of the past set questions, and they're going to give you this angle. What happened was you were given this angle here, asked to find this angle, and what most students did was multiply. Well, divide this angle by a half to get this, but not knowing that they needed to subtract this angle by 360 to get this angle, and then divide this by a half to get this angle here, right? Because again, this angle is the one standing on the same arc as this, not that one. All right, so in a nutshell, be careful. Any angle standing on an arc needs to be facing that arc, right? That you're seeing is standing on an arc needs to be facing that arc. Good. So that's in this scenario. Again, we know x is the center. With our theorem, it's just telling us that if x is the center of the circle and y being x is not the center of the circle, x is the angle at the center of the circle, and y being an angle at the circumference, then x would be 2 times y, twice the angle at the circumference. Of course, again, they're standing on the same arc. In our third circle, same thing. An angle at the center, an angle at the circumference. Again, you just need to look at where those two, the lines that constitute your angle meet. That tells you where your angles are. And of course, the angle they're standing on is here, right there. And they're both facing that angle, so that checks out. Same angle, same arc, with the same arc, angle at the center, angle at the circumference. This theorem comes into play. In no particular order, you need to remember the statements themselves. But so in this statement, very short theorem, one sentence, the angle in a semicircle is a right angle. Right away, that's it. That's it for this theorem. So next theorem. All right, let's explain. So the angle at theorem 2 states, not, I don't want to call it theorem 2. So our second theorem is the angle in a semicircle is a right angle, meaning that it's a 90-degree angle, right? Let me just put that in bracket here, 90 degrees. Okay. So the angle in a semicircle is 90 degrees, or is a 90-degree angle, right? Good. So, and you notice all these terms we're identifying angles. So most of them we're going to be identifying what angles, the relationship between angles. Okay. So here again we have 3 scenarios, and again for all these circles that I have drawn here, O is actually representative of the center of the circle, right? That's the point at which we use to put and draw the circle. Right, good. So we know the center of the circle is O. Any line drawn from one point of the circumference to the center, through the center of the circle to another point, it's what's called the diameter, right? So AC is a diameter, and that's what it's saying here. The line AC is a diameter, therefore it divides the circle into 2 equal segments known as semicircles. Like I've defined before, all diameters separate a circle into 2 semicircles. So AC being a line that's dividing these 2, well, dividing this circle into 2 equal halves, this angle here is actually inside a semicircle, right? Any angle drawn inside a semicircle is 90 degrees by definition. And I'm pretty sure there are proofs to this as to prove why that is so, and I'm not gonna burden you. That's beyond the scope of secondary school maths, right? So any line I could draw any amount of lines in this semicircle, and you see in each of them, or I could even go at the bottom here. Once it's in a semicircle, it's 90 degrees. So all these lines within these semicircles are 90 degrees, 90, 90, 90, 90. Okay. Right. These are all semicircles. They're all 90 degrees. Okay. That's it. A few points to note. Well, this should be obvious to you, but if the angle is coming out of the semicircle, even though, right, this is not 90 degrees, it's not within their semicircle. right? Another thing another way you can write this theorem is that any angle standing on the diameter is actually a 90 degree, because you notice all angles that are in the semicircle stand on the diameter, or they make a triangle with the diameter, right? So any angle standing on the diameter is actually 90 degrees, and that's another way we can actually write this theorem. You notice that for most of your theorems, there's another way to write it. So there's another way to write it. If you will, any angle standing, again, we say it's standing on it. Right? This is our angle. Anything around here, we see it's standing on this thing, right? The angle is standing on this thing, whether it's an arc or a line, whatever it is, it's standing on that, right? That's the terminology we use. So any angle standing on a diameter is actually equal to 90 degrees, or it's a right angle. Right? So you could say once we have these angles, they are 90 degrees, and they make of course, right angle triangles, right, with the diameter. So that one is easy. We don't need to do any calculations. Once you see this, you automatically know what the angle is. So this theorem number 3, says that okay, this is one sentence. But if I were you, I would just copy this, right? This is another way to write it, right? So I actually put 2 ways to write this one, and they're both saying the same thing. Right? So let's go. She's back. A second to come. Right, I'm thinking about Shoshana. Welcome back. Good. So as I was saying, the third theorem, angles at the circumference, again, your angles are either going to be at the circumference or the center. So angles at the circumference of a circle standing on the same arc or chord, if it's standing on the arc, so it's standing on the same chord, are equal. So angles at the circumference that are standing on the same arc or chord are equal. Or, this is another way to put it, angles in the same segment are equal. And this is one usually students don't even write down or don't even take note of. So I usually forget this. But it's the same, these two are actually the same thing. And I'll show you why just now. They're actually saying the same thing. Good. So angles at the circumference standing on the same arc are equal. So if they're standing on the same arc and one is in the center and one is at the circumference, then you know one is twice of the other, right? You'll tell me which one is twice of which later. But if they're both at the circumference, that's where theorem 3 comes in. It says that they're equal, right? They're equal to each other. And that makes sense. Right? That makes total sense. So again, we have our three circle scenario, each showing us a different orientation of this. Again, forever and always, O is the center of the circle in each of these scenarios, right? O is center. Circle. Good. So in the first scenario, angles at our circumference, again, they connect at the circumference. These angles could both connect at the circumference. So they're located at the circumference, and following the angle lines, the angle that they're standing on, already highlighted in green. Actually, I'm highlighted myself. The angle that both of these angles are standing on, angle green and angle green and angle red, are the arc that they're standing on is this arc, right? This arc right here, this portion of the circumference is what they're standing on, right? They're facing this, both of them. So they're both standing on the same arc. They're both on the circumference, then therefore they're equal to each other, right? And you can have them right next to each other like this, or let's erase all of this. Or chord, right? And that's where the or chord comes in. And like I explained, when we look at the first theorem, you can actually draw a line from here to here. Again, both of our angle lines connect at the same point. And if we draw a line here, they're standing on this chord, right? Or you could look at the arc that they're standing on, or you could draw a line from point to point and get a chord, right? Either way, they're standing on the same thing, right? I'm going to use the word thing, right? So they're equal. So x equal to x. Whatever x is over here will be the same angle over here. I look at this second scenario. It brings up something, a theorem that I just pointed out to you. What would be x? See who's focusing and who's not. In scenario number 2, what would be angle x?
90 degrees.
Right. We just so unsure. Anybody sure what angle x is? You sure? You sure it's
Sir, it's 90. Okay.
okay, good, right?
Yes, sir, I'm sure.
Why it's 90? Yeah, why 90?
Because any angle drawn in a semicircle is a right angle triangle. It's drawn on a diameter.
It's on the diameter, right? Or like you said, you rightfully said any angle in a semicircle is 90 degrees. So yes, then these two are 90 degrees. So it makes sense that they're equal to each other, right? However, they're also standing on the same arc, right? Or chord, right? Or chord. The chord is the diameter, right? So they're both standing on the diameter, they would both be equal. So if this theorem wasn't true, then if two angles were in the semicircle, both standing on the same diameter and the same chord, it will cause problems. If this theorem wasn't true, then it would cause problems, right? This theorem would contradict if they were not equal, right? This theorem would contradict that first theorem, the second theorem that I showed you just now, right? So it holds, right? And theorems need to hold because they're facts, right? All theorems need to be facts. And they need to hold true. I am saying facts, I'm using the word facts very loosely there, but they need to hold true, right? So yes, they're both equal to 90 degrees, and they're both equal, again, at the circumference, two angles at the circumference standing on the same chord, which is the diameter, or we can draw in our lines here to see that they're actually on the same arc, right? Good. In our final scenario, we have two angles, one at the circumference over here, one at the circumference over here. Again, we see they're both standing on the same arc. Again, just look at those lines constituting those angles, see where they connect to the circumference, and look at the arc they're standing on, or draw a line from there to there to get their chord. Sometimes the chord is drawn in there for you to help you see. Okay? Sometimes it's not. Depends on how easy the question is. Right? So look at that. So x is equal to x in this scenario as well. Any questions, queries? Please take note of this. Any questions, queries? Fourth theorem, 6 more to go. Now, 6 more to go, technically. 5, right? This is our what? Good. So the opposite angles of a cyclic quadrilateral are supplementary, meaning that they add up to one anything. So what a cyclic quadrilateral is, if you don't know this already, quadrilaterals are 4-sided figures. So what we're talking about is a cyclic quadrilateral is as stated in our epistle here. A cyclic quadrilateral is a quadrilateral, again, a 4-sided shape, having its vertices lying on the circumference of a circle. So a cyclic quadrilateral is a circle quadrilateral, a quadrilateral located inside a circle. But what needs to happen, we need to ensure is that all four vertices, right, these are these points, all four of these vertex points land on the circumference of a circle. Because what can happen and what does happen and confuses students sometimes is that you have a quadrilateral like what we saw before in the first example here. You see a quadrilateral here. This is a quadrilateral, but it's not a cyclic quadrilateral. Right? This is a quadrilateral, but this is not a cyclic quadrilateral, and this is what confuses some students. Simply because, yes, this one is located at the circumference, at the circumference, at the circumference, but this guy over here, not at the circumference. And so it does not count as a cyclic quadrilateral. Wow. I don't know what was happening to my me just now. But it's not a cyclic quadrilateral because of that. Right? So be very careful and check to ensure that all four of your vertices for what you're calling a cyclic quadrilateral are on the circumference. So with that in mind, the definition of a cyclic quadrilateral is a four-sided figure with all its vertices at the circumference of a circle. Okay. Good. Now let's actually get to what the theorem is saying. Right? That is what a cyclic quadrilateral is. Now let's actually get to what the theorem is saying. It says that the opposite angles of a cyclic quadrilateral are supplementary. And we know what supplementary means. We know that the internal angles of a triangle is supplementary, right? Or are supplementary, meaning that they add up to 180. So when we look at a cyclic quadrilateral, again, all four of our vertices are on, let me just show you guys, right? All four of our vertices are on the circumference. It means that the opposite angles opposite each other within our cyclic quadrilateral actually add up to 180. So A plus C should equal 180. And also B plus D should also equal to 180. And that's what this theorem is telling us. Right? So say for instance, A was 80 degrees. I replace 80 degrees over here. Right away, you should be able to tell me what C is. What would C be?
100.
100. Right? 100. Right? Simple maths. Because if they add up to 180, by definition, if I know one, I can just subtract that from 180 to get the other. Right? So same like you would do when you're finding your, right? Same like you would do it when you're finding angles within your triangle. Right? So just keep that in mind. Right? Again, over here, we have another cyclic quadrilateral. Again, this is just a different orientation so that you can still see that this is a cyclic quadrilateral, again, because all four vertices are at the center. And again, it's a quadrilateral because it has four sides. It's a four-sided shape. And this resembles snow. I just need the snow. But yeah, right? This resembles, you could call this a trapezium. Some might look like a, yeah, right? Some you might be able to identify what quadrilateral it is. Right? Nevertheless, four sides tells us it's a quadrilateral, and each side being on the vertex, each vertices being on the circumference tells us it's a cyclic quadrilateral. And again, these opposite angles add up to 180. Okay? So that is what this theorem is stating. Please ensure you take note of the definition of a cyclic quadrilateral in case you didn't know that before. Any questions or queries? All right. So if I was sitting there, a question I would ask is, okay, this is the center of the circle. I says, I keep telling you guys, what's the center of the circle? Good. So therefore, O is the center of the circle, right? So therefore, what we have going on here is a diameter. Right? This is a diameter, which means automatically that this is Right away, you know this is a semicircle. This is half of the circle. Good. So by that definition, would all these angles in the cyclic quadrilateral be 90 degrees? Would these angles be 90 degrees by that definition? Because Theorem 2 says angles within a semicircle automatically 90 degrees. So would these angles in this semicircle be 90 degrees? That would be my question. Want to get at. So it's we can't say that it is 90 degrees. We can't say all of them are going to be 90 degrees, because even though they're angles in a semicircle, like Brianna pointed out, none of them are actually standing on the diameter. Right? In Theorem 2, all of the angles that we were saying are located in a semicircle were actually standing on the diameter. Right? This angle here was standing on the diameter, and in this scenario with our quadrilateral, a cyclic quadrilateral, none of them are actually standing on the diameter. Matter of fact, let me show you guys this a bit better. This angle here is standing, this angle B would be standing on, if I draw a line across, it'd be starting on this line. This is not the diameter. Angle A, so let's find the lines that constitute angle A. And this is angle A. They're all not the circumference, yes, but the angle A is standing on this line, or this arc if you want. So none of them are standing on the diameter, and so that doesn't mean they're automatically 90. They could be 90 because if each one of them were 90, it would still, this theorem would still be true, and that is a possible answer. But you won't be able to say that it is 90 using Theorem 2. So what I wanted to get at is that Theorem 2 does not answer this. Right? We can't use Theorem 2 to get this. It could be 90 or it could not be, and we can't use Theorem 2 to actually get anything concerning these angles, because Theorem 2 doesn't apply here. Right? We can't apply Theorem 2 here. Even though they could be 90, we can't apply Theorem 2 here because these angles are not standing on the circumference. If they were like this, the diameters are circumference. These angles aren't standing on the circumference. I said circumference again, but they aren't standing on the diameter. So this is our diameter. If it was like this, highlighting our diameter again. If it was like this, then of course, right away, you know, this would be 90 degrees because this angle here standing on the diameter, and this would be 90 degrees. All the vertices are on, right? All the vertices are on the circumference, therefore it's a cyclic quadrilateral, right? All these sides here make it a cyclic quadrilateral, and by that definition, we can find that these two sides would be supplementary. And of course they are. 90 and 90 gives you 180, so that checks out.